For all of humanity's technological might, our civilization remains an infant, tethered to the finite, volatile energy of the Earth. But a boundless, clean power source exists, replicated daily in every star: nuclear fusion. This is the reaction that shaped the elements, that created the conditions for life, and it has the potential to solve the energy crisis for all time. To master fusion is to hold a captured star in a cage of magnets, providing the ultimate, sustainable power for our future. What is fusion? It is the opposite of the fission that powers current nuclear plants. Fission splits heavy atoms, fusion forces light atomic nuclei to combine, or fuse, into a heavier one. The process releases a colossal amount of energy because the final nucleus has slightly less mass than the sum of the two initial nuclei. This missing mass is converted directly into energy, as famously described by Einstein's equation, E=mc². The primary fuel for first-generation fusion reactors is a pair of hydrogen isotopes, deuterium and tritium. Deuterium is abundant and easily extracted from seawater, a fuel source effectively limitless for millions of years. Tritium is rarer and radioactive, but it can be bred directly inside the reactor walls using lithium, which is also plentiful. The fusion reaction yields a helium atom, a harmless, inert gas, and a high-energy neutron, carrying the vast majority of the released energy. To force these positively charged nuclei to fuse, they must overcome their natural electrical repulsion, a barrier known as the Coulomb force. This requires immense energy. In the Sun, gravity supplies the crushing pressure needed. On Earth, we must rely entirely on extreme heat. The fusion fuel must be heated to temperatures exceeding 100 million degrees Celsius, 10 times hotter than the Sun's core. At this temperature, the atoms are stripped of their electrons, creating a superheated, ionized gas known as plasma. Plasma is often called the fourth state of matter. It is a highly energetic, charged fluid that reacts strongly to magnetic fields. The fundamental challenge of fusion is not igniting the plasma, but confining it long enough, at high enough density, for sustained energy production. This is known as satisfying the Lawson criterion. The tokamak, the most promising method for plasma confinement, is magnetic confinement fusion, MCF, epitomized by the tokamak reactor design. The tokamak, originally conceived in the Soviet Union, is a donut-shaped, or toroidal, chamber. The plasma is held in place by incredibly powerful, superconducting magnets that wrap around the torus. These fields create a magnetic bottle, preventing the superheated plasma, which would instantly vaporize any solid material, from touching the reactor walls. The plasma is heated through external energy sources, such as microwaves and neutral particle beams. The ultimate goal is to achieve a burning plasma, where the heat generated by the fusion reactions themselves, specifically, the energetic helium atoms, is enough to sustain the reaction without constant external heating. This is the pathway to scientific break-even Q=1 and, eventually, a net energy gain Q greater than 1. The global effort to master fusion is centered on several revolutionary projects. The most ambitious is ITER, International Thermonuclear Experimental Reactor, currently under construction in France. This massive international collaboration aims to be the first device to demonstrate the scientific and technological feasibility of fusion as a large-scale power source. Its goal is a fusion gain of Q=10, 10 times more power out than the power put in to heat the plasma. A competing approach is inertial confinement fusion, ICF, pursued famously at the US National Ignition Facility, NIF. Instead of magnetic fields, NIF uses nearly 200 of the world's most powerful lasers to compress a tiny, pea-sized fuel pellet for a few billionths of a second. In late 2022, NIF made history by achieving ignition, demonstrating scientific break-even for the first time by generating more energy from the reaction than was delivered by the lasers. Despite these breakthroughs, the journey to a commercial fusion power plant is fraught with immense engineering hurdles. Materials science, the intense flux of high-energy neutrons released by the reaction bombards the reactor walls. We must develop materials, like advanced ceramics or specialized steel alloys, capable of surviving this extreme neutron damage for decades without becoming brittle or overly radioactive. Tritium breeding, we must design efficient breeder blankets within the reactor walls to reliably produce the required tritium fuel from lithium, ensuring a closed and self-sustaining fuel cycle. Heat extraction, the kinetic energy of the neutrons must be efficiently captured by the reactor's coolant systems and converted into usable heat to spin a turbine and generate electricity, a critical system engineering challenge. Plasma control, the superheated plasma is notoriously unstable, prone to sudden, catastrophic drops in confinement known as disruptions, which must be accurately predicted and suppressed. The successful development of commercial fusion power would be the single most transformative technological event of our era. It offers a future where energy is plentiful, clean, and inherently safe, with no risk of runaway reactions and minimal long-lived radioactive waste. Private companies are now joining the race, accelerating research with the goal of connecting pilot plants to the grid within the next decade. Fusion power represents true energy independence, freeing us from the environmental cost of fossil fuels and empowering every facet of our cosmic ambition. The stellar furnace is being built on Earth, and when it is finally lit, the age of scarcity will end. For our final episode in this series segment, let's explore one of the most commercially valuable futuristic projects, asteroid mining. We'll discuss the incredible wealth, the engineering challenges, and the geopolitical implications of exploiting the resources of the asteroid belt.